Hi, good afternoon. My name is David. I'm a student at the Instituto Tecnológico de Orizaba. And well, this video is made for the class of physical chemistry imparted by the teacher Eric Figueiras. And well, today I'm going to talk to you about colligative properties. First of all, we have to know what is a colligative property. Okay, a colligative property is a property of a solution that is dependent on the ratio between the total number of solute particles in the solution to the total number of solvent particles. Colligative properties are not dependent on the chemical nature of the solution's components. Thus, colligative properties can be linked to several quantities that express the concentration of a solution, such as molarity, normality, and molality. The four colligative properties that can be exhibited by a solution are: first of all, the boiling point elevation; second, the freezing point depression; third, the relative lowering of vapor pressure; and fourth, the osmotic pressure. I am going to explain to you each one of these properties that I have mentioned, that are four. And well, we're going to start by talking about the boiling point elevation. Okay. Well, first of all, the lowering of vapor pressure. In a pure solvent, the entire surface is occupied by the molecules of the solvent. If a non-volatile solute is added to the solvent, the surface now has both solute and solvent molecules. 30B fraction of a survey covered by solvent molecules gets reduced, since the vapor pressure of the solution is solely due to a solvent alone. At the same temperature, the vapor pressure of the solution is found to be lower than that of the pure solvent. Well, now that I have told you this little explanation, I'm going to put in the video a little picture that is going to show better this. Well, it's an example, okay? Well, as we can see in the image, the first cylinder is filled with a pure solution and has an atmospheric pressure, okay? And the second cylinder is filled with a solute, and well, it has a lower vapor pressure. Okay, if P0 is the vapor pressure of a pure solvent and PS is the vapor pressure of the solution, the difference PO-PS is termed as a lowering in a vapor pressure. The ratio PO-PS above PO is known as the relative lowering of vapor pressure. Rold in 1886 established a relation between relative lowering in vapor pressure and the mole fraction. The relationship is known as Rolld's law, which I have talked in another video, and it states that the relative lowering in vapor pressure of a dilute solution is equal to the mole fraction of the solute present in the solution. If n moles of solute is dissolved in n moles of the solvent, then according to Rolld's law, PO minus PS above PO equals n above n minor plus n. Then we have the second colligative properties, that is the elevation in boiling point. The boiling point of a liquid is the temperature at which the vapor pressure is equal to atmospheric pressure. We know that the addition of a non-volatile liquid to a pure solvent, the vapor pressure of a solution decreases. Okay? Therefore, to make vapor pressure equal to atmospheric pressure, we have to increase the temperature of the solution. The difference in the boiling point of the solution and the boiling point of the pure solvent is termed as the elevation in boiling point. If T0B is the boiling point of the pure solvent and TB is the boiling point of the solvent, then elevation boiling point is given as the difference in TB equals T0B minus TB, okay? So now, experimental results show that there is a relation between elevation in boiling point and molality M of the solute present in solution. We have, under this explanation, an equation that says that the difference in TB equals KBM, where KB equals to the molar elevation constant. Substituting the value of M in the above relation, we get the difference in TB equals 1000 for KB for square meter between square meter for meter, where M2 equals the mass of solvent in grams, M1 equals the mass of solvent in kilograms, and M2 equals the molar mass of a solute. Then we have the third colligative property, that is the pressure in freezing point. The freezing point of a substance is defined as the temperature at which the vapor pressure of its liquid is equal to the vapor of the corresponding solid. Okay, according to Rolle's law, when a non-volatile solid is added to the solvent, its vapor pressure decreases, and now it will become equal to that of solid solvent at a lower temperature. Okay, the difference between the freezing point of the pure solvent and its solution is called depression in freezing point, which explains our third colligative property. Okay, so now I'm going to give you an explanation of the equations of the depression in freezing point. So now for the explanation of the depression in freezing point equation, we have if T0F is the boiling point of the pressure of the pure solvent and Tf is the boiling point of the solution, then depression in freezing point is given as the difference in Tf equals T0F minus Tf. Just like elevation in boiling point, depression in freezing point is also directly related to molality M, where we have the difference in Tf equals 1000 for Kf for square meter above M2 for M1, where Kf equals the molar depression constant, M2 mass of a solvent in grams, M1 mass of solvent in kilograms, and M2 molar mass of solute. And finally, we have our fourth colligative property, okay? That is the osmotic pressure. When a semi-permeable membrane is placed between a solution and solvent, it is observed that solvent molecules enter the solution through the semi-permeable membrane and the volume of the solution increases. Okay? The semi-permeable membrane allows only solvent molecules to pass through it, but prevents the passage of bigger molecules like solute. This phenomenon of the spontaneous flow of solvent molecules through a semi-permeable membrane from a pure solvent to a solution or from a dilute to a concentrated solution is called osmosis. The flow of solvent molecules through the semi-permeable membrane can be stopped if some extra pressure is applied from the solution side. This pressure that just stops the flow of solvent is called osmotic pressure of the solution. Now, I'm going to show you a little diagram that is going to give a better explanation of this. Okay, so as we can see in the image, we have in the first part an equal part of pure solvent and an equal part of pure solution. And between them, we have a semi-permeable membrane. Okay, so when we add more solution, we're going to see that the semi-permeable membrane only gives us the increase in pure solvent, but just gives us a more concentrated solution, okay? And well, then it is completely in balance again. We know that osmotic pressure is a colligative property as it depends on the number of solute present and not on the nature of the solute. Experimentally, it was proved that osmotic pressure P is directly proportional to molarity C and temperature T. Mathematically, P equals CRT, where R is the gas constant. Here, B is the volume of solution in liters and N2 is molecules of solute. Okay, I am talking about the equation that is shown above. And if M2 is the weight of solute and M2 molar mass of solute, then N2 equals M2 between M2. Thus, by knowing the values of P and W2, temperature and volume, we can calculate the molar mass of the solute. Okay, and then we have three different solutions where the osmotic pressure can be applied, or the fourth colligative properties. The first of them is the isotonic solution, that are two solutions having the same osmotic pressure at a given temperature that are known as an isotonic solution. When such solutions are separated by a semi-permeable membrane, there is no osmosis. Okay? The next one is the hypotonic solution. A hypotonic solution has a lower osmotic pressure than that of the surrounding. The concentration of solid particles is less than of the surrounding. If the hypotonic solution is separated by a semi-permeable membrane, then water moves out of the hypotonic solution. And then we have finally the hypertonic solution. A hypertonic solution has a higher osmotic pressure than that of the surrounding. The concentration of solid particles is more than that of the surrounding. If the hypotonic solution is separated by a semi-permeable membrane, then water moves inside the hypertonic solution. As we can see in the hypotonic solution, there is no pass of water to the solution, okay? Then in the isotonic solution, we have a medium, barely none, pass of water to the solution. And in the hypertonic solution, we can see that the water has a complete and full access to the solution. And also, we don't have to forget, if we are going to talk about colligative properties, we can't skip talking about the Bandt-Hoffe factor. The Bandt-Hoffe factor is when the solute undergoes dissociation or association in the solution, the number of particles in the solution decreases, and thus colligative properties changes accordingly. The extent of dissociation or association of the solute in a solution can be expressed by a factor called Bandt-Hoffe. Okay, so we are going to calculate the Bandt-Hoffe factor that is said by an equation that is I equals to the observative colligative property between the theoretical or normal colligative property, and also can be explained as the number of particles after dissociation or association between the number of particles when there is no dissociation or association, and also can be explained as the normal molecular mass of the solute between the observed molecular mass of the solute. Also, it's on me to tell you that there are three categories of solute properties according to Ostwald. Wilhelm Ostwald introduced the concept of colligative properties in 1891. He actually proposed three categories of solute properties. That is the number one, that is the colligative properties depend only on solute concentration and temperature, not on the nature of the solute particles. Then the number two is that the constitutional properties depend on the molecular structure of the solute particles in a solution. And the number three, that is the additive properties, are the sum of all the properties of the particles. Additive properties are dependent on the molecular formula of the solute. An example of an additive property is the mass. Well, now I'm going to show some examples where the colligative properties are used to solve them, okay? Now we have the first example, which says the molar elevation constant for water is 0.513 centigrades for kilograms per mole. When 0.2 molecules of sugar is dissolved in 250 grams of water, calculate the temperature at which the solution boils under atmospheric pressure. Well, for the solution, we have that the elevation in boiling point can be written as the difference in TB equals the moles of sugar for 1,000 between weight of water in grams. So, substituting, we have the difference in TB equals to 0.2 by 1,000 between 250 equals 0.8. For pure water, the T0B equals at 100 centigrades grade, okay? So the TB equals at 100.80 centigrades. Our second example says, if we have a solution of calcium chloride was prepared by dissolving 0.0169 grams in 1 kilogram of distillated water, which has a molar mass of 41 grams mole and the chloride 35.5 grams per mole, the molar depression constant of water is 2 kilograms mole. The depression in freezing point of the solution is, and well, we have the solution of this problem here, which says that we have to calculate the band Huff factor of CaCl2 is 3, that equals 3. Then we have the K, that Ka equals to 2 kilograms mole. Given mass of C of calcium chloride equals by the M2 equals 0.0169 grams. The molar mass of calcium chloride by the M2 equals 100 and 112 grams, and the weight of water equals the M1 is 1,000 grams. So the difference in TF equals Y by 1,000 by Kf by M2 between M2 by M1, which is a result of exponential 9 minus 4. For the example number 3, we have that hexane and heptane were mixed to form an ideal solution. At 100 centigrades, the vapor pressure of two liquids, hexane and heptane, are 190 kilopascals and 45 kilopascals respectively. What will be the vapor pressure of the solution obtained by mixing 25 grams of hexane and 35 grams of heptane will be? And we have the solution in here, that is the number of moles of hexane that is written as N1 equals to 25 between 86, that equals 0.29, and then we have the number of moles of heptane that is written as N2 that equals 35 between 100, that equals 0.35. Then we have our equation here that says that x1 equals n1 between n1 plus n2. So we have all the calculus in here, and we have a result of 0.45. And for x2, we're going to reduce 1 by 0.41, which gives us a result of 0.55. And then we have that P equals a P01 x1 plus P02 x2. And we have in here the numbers that says 1900.45 plus 450.45 equals 110 kilopascals. And then our fourth example is a theoretical example that says, on adding non-volatile solute to a solvent, which of the following effect is observed? A. Increasing in vapor pressure. B. Increasing in freezing point. C. Decreasing osmotic pressure. And D. Decreasing vapor pressure. So, according to what I have said in this video, the solution is the option D. In a pure solvent, the entire surface is occupied by the molecules of the solvent. If a non-volatile solute is added to the solvent, the surface now has both solute and solvent molecules. Thereby, fraction of surface covered by solvent molecules get reduced since the vapor pressure of the solution is solely due to the solvent alone. At the same temperature, the vapor pressure of the solution is found to be lower than that of the pure solvent.